Okay, last time we were having this discussion about the interpolation topic. So, for example, we started from interpolation, the concept of interpolation, and there are two approaches. One is the Newton polynomial, the other is the Lagrange polynomial. Both approaches are essentially the same. That means their results will be the same. So we started from the Newton polynomial, which is the full name is the Newton's divided difference interpolating polynomials. So this polynomial is about the finding the divided differences. Okay, so we did two examples. One is for the linear interpolation, and the other is for the uh, quadratic interpolation. Okay, so for the quadratic interpolation example, we can also do on Excel as well. Okay, so for example, if you see that if we have this same data like before, X and Y, and Y in this case was log of X. Okay, and we took the values of 1, 4, and 6, and then their log of their true values are log of this value. Okay, and then I have these values. So these are the given values. So if X and Y, the values are given as like this. So by the divided difference interpolation, find the value of log of 2. Okay, so then we have to find log of 2 by interpolation. Okay, so this was the so in the Excel approach, we can organize the information in the form of the divided differences. So we will find the divided differences. So we will find the first divided differences. So maybe I can write like 1 dd. So first divided difference. So first divided difference will be the difference of these two y values and divided by the difference of these two x values. Okay. And that will be placed here. Okay. And the second one will be placed here. Second first divided difference will be placed here. That will be the difference between these two values and divided by the difference between these two values. So this we can very simply provide it on Microsoft Excel. So it will be, first we will select this column minus B2 column, B2 cell divided by cell A2, A3 minus A2. And then I will calculate it. So we need to calculate one more divided difference. So I will just drag it down. So it will be 0.2027. So since there are three values we have, so there will be two first divided differences. Then in the second divided difference, it will be the difference between these two values. It will be the difference between these two values and the difference between not these two values of x, and it will be the difference between this and these values, these and these values of x. Okay. So this is the difference of the difference. This is the difference of the difference. So in this case, it will be this value minus the this one, that is C3 minus C2 divided by, so since this is the second divided difference, so it will be the third value in the x. Okay, third value in the x minus the first value in the x. So it will be represented like this. So that is why you can see that in over here we represent these like these terminologies. So this is the difference between x2 and fx1 divided by x2 over x1. And then x3 minus x2 divided by x3 minus x2. This fx4 will be x4 minus x3 divided by x4 minus x3. So this is the first divided difference. The second divided difference will be this value, x3, x2, x1, and then their extreme x values, x3 minus x1. Similarly, for this x3, x4, x3, x2, and divided by their extreme x4 and x2 values. And similarly for the third divided difference. So in this example, which is we are taking for example number 2 by the divided difference method. So we get these values in this divided difference table. So when we have only one value over here, then we have actually found out the coefficients B0, B1, and B2. Okay, so these are the coefficients B1, B0, B1, and B2, which are needed for the interpolation. Okay, and what is that equation which uses B0, B1, and B2? It is this equation. Okay, it is this equation. F2's x is equal to B0 into B1 into x minus x0 plus B2 into x minus x0 and then x minus x0, x1. So this is the equation. So here I have this equation. So using this equation, now I can find the value of log 2 because we know the value of B0, which is 0, the value of B1, which is 0.462, and we have the value of B0, which is minus 0.051. Okay, and the values of x0, the values of x0 and x1 are x1, 1 and 4 respectively, and the value of x is the one that is 2, which is we want to find 2. So in order to calculate it, so maybe we can just calculate x minus x0 here. We can calculate x minus x1 here. So these are the two x minus x values that we need over here. Okay, and here we can calculate the f of x. Okay, in this case, f2 of x because we are finding the quadratic polynomial. Okay, so and what is x? X is 2. Well, x is 2. So here we have we can find x. X is 2 over here. X is 2 over here. So what will be x minus x naught? X will minus x naught will be 2 minus x naught. X naught is this, the first value in this x. So this is x minus x naught. And then this 2 minus this x1 value. So this is x minus x1. So now we can I can now input these formula over here. So it will be equal to b naught. So here we have the value of b naught and plus b1 times x minus x naught, which is this value, and plus b2 times x minus x naught times x minus x1. And now I hit enter, and then here I will find the answer, which is 0.565844, which is the same answer which we got in this example 18.2, 0.565844. Okay, 565844. So this is how we can apply the divided difference formula, divided difference approach in the Microsoft Excel. Is it clear?
Yes.
All right. So this was the divided difference. So in this case, the percentage relative error is 18.4%. Okay. In earlier case, it was more. So here we have this quadratic estimate. So this blue curve is the quadratic curve which we obtained here, and this quadratic curve is better than this linear estimate. So we did the linear interpolation, we did the quadratic interpolation. So we can expand it for nth order interpolation. So the approach will be the same. It will consist of finding the divided differences. So we have the general equation b1 into b2 into x minus x naught, and then bn, like that. So b1 will be f of x1, b2 will be f of x2, x1. That means this in this case we are showing it with the help of square brackets. So instead of the parentheses, we are showing the square brackets over here, which means that it is not the value of the function, it is the value of the divided differences. So the divided difference x2 minus x1 will be then fx2 minus fx1 divided by x2 minus x1. So the divided difference x3, x2, x1, this is the second order divided difference, and it will be equal to fx3 minus fx1. Sorry, it will be equal to fx2 minus fx. That is, it will be the divided difference between fx3, fx2 minus fx2 minus fx1 divided by x3 minus x1. Okay, the formula will be like that. So here it will be like that formula. So as we can see it from the from this table of the finite divided differences. Okay. So let's see one more example. This time we can do we can take a fourth data point, and then we can find it up to the third divided differences. So we can say take the same example like this one before. Yeah, here. So instead of one more point, yeah, so we can take one more point. Instead of 3 points, now we have 4 points. So we take another point as f. Okay. And let's recalculate these values. And in this case, the equation which we will need is this one. So although we are doing it in Excel, but I think it is also useful to do it in hand calculations as well. Yeah. So this type of approach may be even useful to do in the hand calculation. So we need this. Okay, so this is the equation we need. So in this case, for the third order polynomial, so we need this equation b0, b1, b2, and b3. So we need 3 coefficients, b1, b2, b0, b1, b2, and b3. And then these multiplying polynomials, x minus x0, x minus x1, and x minus x2. So in this case, we will need b3 as well, which will come from the third divided difference. Okay, third divided difference. And the values of y are actually given as the real values of the log of x. And here we can calculate it like this. Maybe we can drag it up to here. Okay, so the first divided difference is now this value minus this value divided by this value, and this value minus x naught. So once we calculate it, then we can, it is the advantage to us, we can just drag it down to calculate these all the other values. Okay, the second divided difference is equal to this second of the first divided difference minus the first of the first divided difference divided by x2 divided by this x2 minus x1, and then bracket close. So it is this value. And then I will just drag it down. So it will be minus 0.003. And the third divided difference is equal to the second of the second divided difference minus first of the first divided difference divided by, since this is the third divided difference, I will start from the fourth value in x. So 1, 2, 3, 4, which is 6, and minus first value of x. So it will be this. So this will be the third divided difference. So in this case, I have found very quickly these coefficients b0, b1, b2, and b3. Okay, so now I need these multiplying polynomials, x minus x naught, x minus x1, and x minus x2. So x minus x naught, x minus x1. The next I need to find is x minus x2, and then f of x. Finally, which will be the answer. So in this case, it is x minus x naught is this 2 minus x naught is this, and then this is 2 minus x1, and then this is equal to 5 minus this is equal to this 2 minus x2, that is, which is 5. So minus 3. So we only need these values, right, over here. And then we can find now f3 of x. So f3 of x starts from b0. b0 is in this case 0. Okay, remember that b0 is 0 only in this particular case, because the value of this log of 1 is 0. Okay, you should not make a conclusion that it will always be 0. For some other data set, it will have some value which will be other than 0. Okay, so this is not a general solution that b0 is 0. b0 can be other than 0 as well. But in this example, we are using it. It is given as 0. Okay, so this is b0 plus b1 times x minus x naught plus b2 times x minus x naught times x minus x1 plus b3 times x minus x naught times x minus x1 times b3. So time, not b3, it is x minus x naught. Okay, so I have input this formula for the f of x, then I will calculate it. So it will be 0.6287. So which will be the same answer which have been obtained by manual calculations in Excel, which is 0.628786. But here in this case, in this Excel format, we can very conveniently calculate it by creating the forward difference table. So it is 0.628769. This is the answer in this case. So which is the this is the interpolated value of this function for 2. So interpolated between 1 and 4 as 0.62 for a value of 2. Okay. So in this case, the percentage error is now 9.3%. So as we can see that we are doing the greater is the order of the polynomial, less and less is the percentage error. So this percentage error we can find because from the true value. So the true value for the log of x is, that is the true log of 2. Okay, so true log of 2 is equal to log of 2. So this is the calculated value, this is the true value. So the true error is, true percentage error is ET is equal to true value, which is this, minus the calculated value divided by the true value, and multiplied by 100. We need one bracket here. So it is 9.27, 9.29, 9.27, 9.3%. So the complete cubic polynomial is shown in this figure. Yeah, so this is the complete cubic polynomial. Okay, so this complete cubic polynomial is shown over here. So as you can see that if we have this polynomial, which is in this form, and if we plot it, over here, then it will give us some values. So now it is almost quite close to the true value. Okay. But for higher values, I think we need some more values over here. So here in this case, for example, if we need the value, if we need to interpolate the value at here, this cubic polynomial is actually offshooting from the true result. So therefore, we should have other data points over here between these two values. Okay, so the meaning is that if we want to interpolate between 5 and 6, yeah, then it should be okay. But if we want to extrapolate it, so for example, we want to find the value at 7 from here, then we should have the points around that point 7. So therefore, maybe log of 10, log of 9. So that this 7 is in between these given points. Okay, so then we can better interpolate it. Otherwise, as this chart shows that after this, it is diverging from the true value. Okay. The interpolating function is diverging. Okay, next is the next approach is the Lagrange interpolating polynomial. This is another form of the divided difference polynomial method. But the answer from both approaches will be the same. The answer from both approaches will be the same, but only thing is this is the other form of the same interpolation method. So the Lagrange interpolating polynomial is simply a reformulation of the Newton's polynomial that avoids the computation of the divided differences. So simply, we don't want to find the divided differences in this case. So if we don't find the if we don't calculate the divided differences, So what do we calculate? In this approach, we just calculate the multiplication of the ratios. Okay, we calculate the multiplication of the ratios, and then multiplication of the ratios is represented by this multiplication symbol. So this is the symbol of the multiplication or the product. Okay, so we simply find the product of the ratios, and the ratios are x minus xj and xj minus xi minus xj. So the variation is from I is equal to 0 to n, and where Li is the Lagrange ratio, Li is the Lagrange ratio, and this is multiplied by the value of the function. So if we have the data points x0, x1, x2, and their corresponding f values are x0, fx2, fx1, fx2. So we can rearrange these terms in this format, and then we can find these products. So these products then go like this. So it will be, for example, we will start from I is equal to 0. Okay, so we will start from I is equal to 0. So, and then it will be x minus x0 divided by x0 minus j. Yeah, in this case, it will be j will be not equal to 1. Okay, so it will go like this. So anyway, we can represent these Lagrange second order polynomial like this. So and first the first order polynomial, and then the Lagrange second order polynomial. So the formulation can be derived from the divided differences, and then this formulation, the derivation of this divided difference is given in this textbook. It is a little bit I mean it's easy actually. The derivation, if we have the divided differences formulation, then we can convert it into the Lagrange formulation, and with a little bit of algebra, and then we can convert those divided differences formulation into the Lagrange formulation. So the linear for the first order, the formulation is like this. It is for the first order, we need the function values of the functions at x0 and x1. So the values of this function at x0 and x1 are respectively being multiplied by x minus x1. So here you can see that in the numerator, x0 is not present. Okay, but here we are multiplying it with the x0, and in the denominator there is the presence of x0, so it will be x0 minus x1. And similarly for the second term, we have seen that it is fx1, and then there is no presence of fx1 in the numerator. So x1 is present in the denominator. So it will be x1 minus x0. So x is here, the x is replaced by x0 in the denominator, and here the x is replaced by x1 in the denominator. So this is for the first order Lagrange polynomial. In the second order Lagrange polynomial, so we have respectively like two of the products for the Lagrange coefficients. And then we have total three terms, fx2, fx0, fx1, and fx2. So the coefficient for fx0 is does not involve x0 in the numerator. So similarly, the coefficient of fx1 does not involve x1 in the numerator. So this is for you to remember. So how you can remember it? Okay, and then simply we are replacing x with the x0 in the denominator over here. Okay. So once you set up the numerator, then you can replace it with x naught. So with this thing in mind, maybe we can write it for f3 as well. Okay. So for example, for the f3, it will be, so f3 of x, it will be, how many terms there will be in the f3 of x? First of all, yeah, how many terms will be there in f3 of x? So for example, if I want f3 of x, well,
4.
yeah, there will be 4 terms. There will be 4 terms. Okay. So if, for example, if I want to write here, yeah, maybe I can write. So if I want to write f3, yeah, it's not writing actually. I don't know. Maybe I try to write it in Word. If it is f3, okay, f3 of x will be equal to, then, so the first term will be f of x naught, okay, and then its Lagrange coefficients will be x minus x naught, x minus x1. No, I think there will be some difference, because in the numerator there will be no x naught term, so it will be x minus x1, okay, x minus x2, and x minus x3, okay, and then it will be, now here in the denominator all of these terms will be the same. The only difference will be that x will be replaced by x naught minus x1, x naught minus x2, and x naught minus x3. So this will be the first term for the f3 of x. The second term will be f of x1, and then can you tell me what will be the numerator? Tell me what will be the term in the numerator? So for f of x1, no x1 term will be involved. So it will be x minus. Is anyone listening?
X naught.
Yeah, yeah, x minus x naught, x minus then
X2. X2.
yeah, and x minus
X3.
X3.
3. Yeah, so no x1 term will be involved. And then in the denominator, as a rule, x will be replaced by the x1.
X1.
x1 minus x naught, x1 minus x2, x1 minus x3. And similarly, then fx2, so it will be now Okay, do it one more time.
X minus X naught.
X naught, X minus
X1.
and X minus
X3.
X3. Yeah, there will be no X2 term. So here, but X2 term will come over here. X2 minus X naught, X2 minus X1, X2 minus X3. And similarly, there will be X3. So that will be X minus X naught, X minus X1, X minus X2. So there will be no X3 term in the numerator. But here in the denominator, X3 minus X naught, X3 minus X1, X3 minus X2. Okay. So in this way, you can write the Lagrange polynomial function for up to f3 of x. So, okay, so these are the f1 of x, f2 of x, and then we have written for the f3 of x over here. So a visual depiction of the rationale behind the Lagrange polynomial. So since this figure shows a second order case, each of the three terms is a parabola that passes through one of the data points and is zero at the other two. So the summation of the three terms must therefore be the unique second order polynomials that passes exactly through the 3 points. Okay, so that was about the Lagrange polynomial, and then let's look at one example for the Lagrange polynomial, say maybe for the second order. So similarly, we can do it on Microsoft Excel, okay? So let's do it over here. X, and then y is equal to log of x. So we took this frame function. So we took the values at 1, 4, 5, and 6. Okay, let's do it the third order Lagrange. I think it will be a little bit lengthy. Let's do it for the second order only. Maybe we don't have enough time. So let's do it for the second. So we take only 3 points, 1, 4, 6, and this is this one, and these are the given values. Okay. So these are the given values. Okay, so now in this Lagrange polynomial, we have this formula. So although we know the form of the formula, so the formula is like this, Lagrange. So this is the first order, okay? So maybe we can do the second order as well. Yeah, this is the formula. Yeah, so for these Lagrange polynomials, so what we need is the Lagrange coefficients, L's, okay? So, and then we know that we have this fx naught. So this is f naught, this is f1, and then this is f3, all right? And then for these Lagrange polynomials, we need x minus x2 and x naught minus x1 like that as well. So what we can do is we can calculate these values which we need over here. So we need, so these are the Lagrange LIs, okay? Yeah, these are the Li of x that we need to calculate. So, but for calculating Li of x, we need x minus x1, x minus x2, x naught minus x1, x naught minus x2. So I think there may be some ways we can do it, but what we can do is first we can calculate separately these values. Okay, so what we need is, for example, this is the value of x that we want to interpolate. Okay, so for this, maybe we can put it over here. I'm just thinking about what will be the form of this calculation on Microsoft Excel. So so what we need to start from x minus x1, then we need x minus x2, okay, and we also need x minus x naught, okay. So, and then we also need x naught minus x1, so which is x naught minus x1 is the same as the x minus x naught, that is only with the opposite sign. And what else we need? X. So for example, x minus x1, x minus x2, x minus x naught we have calculated. And then we have without x, okay, x naught minus x1. So we need x naught minus x1. We need x naught minus x2. Sorry. And we need x1 minus x naught, or x1 minus x2 as well, right? x1 minus x2. So it seems that it is not very convenient to do it on Microsoft Excel. So yeah, sometimes Microsoft Excel maybe it will be confusing over here, or maybe we can just try to do it like over here. So for example, if I want to calculate this coefficient Li of x, so it will be x minus x naught into x minus x2. So it will be equal to x minus x naught. So x, what is x? X is this, minus x naught is this. No, it is not x naught, it is x1. X minus x1 times x minus x2. So this is x minus x2, okay. And then divided by, now inside of the bracket, x naught minus x1. So this is x naught minus x1 multiplied by then x naught minus x2, and then bracket close. So this will be the coefficient over here. Okay, so for this one, what we have is x minus x naught. So x minus x naught multiplied by x minus x2, x minus x2 divided by x1 minus x naught. So this is x1 minus x naught multiplied by x1 minus x2, which is x2. So we get this, okay. And then the third one is equal to x minus x naught, x minus x naught multiplied by x minus x1 divided by x2 minus x naught. So x2 minus x naught multiplied by x2 minus x1. Okay, so we get this minus 0.2. So now simply we have to multiply these two values and then add them together. Okay, I think this is now not needed. Okay, this one. So Li of x, Li of x times f of x. This is the multiplication of these two multiplied by these two. So it will be 0 and then it will be over here. And then I will add it. Okay, so then finally we have to add it. So it will be 0.565844, which is the same answer as we can get from this calculation. So okay, they did it for the first order, and then for the second order is this one, 0.565844. So in this way, then you can do it on by manually. So here, but in this case, for the hand calculation, it is much easier to remember. So if you can see that in the numerator, you don't take that x value for which you are multiplying by the function, okay? And then input these values, and then we can find the values. In the denominator, then you replace this x value with that x naught, and you replace this x value with x1, and like that. So by this approach, we can just remember and visualize this formula, how these values are input. And then once you input these values, and then you can calculate it. So the answer is exactly the same, because there is numerically, uh, 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 mathematically, there is no difference between the core of these two values, core of these two methods, the divided difference and the Lagrange method. All right, so this was the Lagrange method which we covered today. So in the third main method over here in this topic is the supply interpolation. So this supply interpolation we will cover in the next class on Friday.
Okay.